Why the parser problem exists? This is subtle. You ask deep questions about scanner, parser, runtime. This section connects them. Problem: parser a equals to 5. At first, it parses a. That looks like a normal expression r dash value. But later, equal. Now we realize, oh, this wasn't a value expression. It's a location I dash values. So basically, the only time we will be able to recognize that it is an I value or a location is if the parser encounter the equal. But at first, when the parser see the A, it will look like a normal expression like R value. Core issue: the parser doesn't know it's an assignment until it's too late. Why this matters deeply? Because syntax does not directly encode meaning. You sometimes need context and look ahead. So just a syntax alone, letter 8, does not encode meaning, obviously, right? Because words, kind of like in language, words alone could have could be are often more confusing than a sentence, because a sentence tell you what's the meaning is. So it's the same with this. Syntax does not directly encode meaning. You sometimes need context and look ahead. This connects directly to your runtime error questions. Let's tie it all together. Case 1, an initialized variable, print a semicolon, interpreter tries to evaluate a as R value. Second, it needs a value. Third, none exist, runtime error. So it evaluates the A because it prints A, but since A is not initialized or doesn't have a value, therefore cannot be evaluated too. Therefore, it produces a runtime error. So that's a very simple R value, which defines the irregular expression, not really the location. But what about those that has location, such as the one that has value, such as this assignment, so a equals to 5. Interpreter first treat a as I dash value. Second, finds storage. Third, assigns. So that's actually what it's doing in the simple assignment. First, it treats the letter A as actually a location value, and then it finds that location where it is in the storage, and then third, assign the 5 value. Final connection: the same syntax A behaves differently depending on context. If it as value, it needs data. If it as location, it needs storage. 6. Your subtle misunderstandings precise. First, errors are about memory or hardware. Wrong level. Correction: errors here are about invalid evaluation of expressions, value versus location mismatch. So the runtime error that we really see in interpreters is not a memory or hardware leaks. It's really about how the language again imposes meaning depending on what you provided, such as a value or location mismatch. Second, variables equal memory slots. Too simplistic, better. Variables are bindings in an environment which may map to memory. So just because it's variable doesn't mean it occupies a memory slot, because remember, because of the control flow construct, some of those variables would not actually run unless some outside or some dependent behavior comes. So it's a binding to that environment or to that scope. So in the future video, we will discuss more about scope and how this and also the environment, how the class, how do we actually create that environment, and what are usually the rules when dealing with those environment. Third, everything evaluates to a value. This section disproves that. Correction. Some expressions evaluate to location, like the I values. So that expression does, it's like with statement. So this is a deeper understanding of statement. Remember, statement hold location. It doesn't really evaluate or do computation. It doesn't evaluate a value. So this is what this chapter disproves. Fourth, parser just reads syntax. Too shallow. Correction, parser is trying to infer semantic structure from syntax with limited information. So the parser does not actually just read syntax. So it has limited information, but still it needs to be able to um, produce meaning out of those limited information from the code that the programmers write. Fifth, missing delayed interpretation. You then explicitly realize the parser initially misclassifies A and fixes it later. This is huge. So the delayed interpretation, as we can see, since it's a dynamic type, it didn't check that at compile time. It only see that at runtime. So that's the delayed interpretation of this interpreter. Seventh, the trick why the parser works anyway. The book does something clever. First, parse left side as normal expression. Second, if equal appears, reinterpret it as assignment. Then check if left side is valid I value. So that's the algorithm that we will discuss in the future video. So first, it parses the left side as a normal regular expression. Then if equal appears after that regular expression, then it will reinterpret that as an assignment and check if left side is a valid I value or regular expression. Now deep inside, parsing is sometimes speculative, then corrected. So it changes based on what it sees after the left or after parsing the left syntax. So how this connects to hardware, your favorite layer. Let's ground it. When you do A is equals to 5, semicolon, eventually becomes store 5 to address underscore of A. So that's another like explanation of that. You would store the value of 5 to the address of A. So when you do print A, it becomes load value from address underscore of A and then prints it to the screen. So that's how we kind of convert that to an assembly into an actual CPU that does the actual calculation. Final hardware connection concept. I dash value, hardware equivalent, memory address. Concept, R dash value, hardware equivalent, data in memory. So again, that's their difference. The R value, the regular expression, is actual data in memory, while the I value is just the address without any data. So assignment, write instruction. So assignment, the equal sign is actually a write instruction. Like put this or update this value of this memory address. Variable read, load instruction. So variable read such as print A, when we read an actual variable, that's actually what we do. We load that from the memory address where it is from and then put that in the print of the screen. So final corrected model, this is the one you need. Evaluation is not just values. Expression, either value or value or location. I dash, I don't know if it's I, it's actual, I think it's L value. Yeah, it's L value, sorry, because it's for location, L value. So again, an expression or a regular expression is not just one type, it's actually a two type. So assignment L value is equals to R value. So this is how we do the assignment. So moving forward, you can think of your code as actually like this. You have an L value at the left side, assignment equal, which is just you call that write instruction. So you would write this R value into this memory address. So that's what it is. So another way of explaining this L value is actually the identifier, because usually you have an identifier for variable or function. Runtime error occurs when expected value got nothing, expected location got value. So that's a runtime error because you got those location instead of a value. So that's actually how our code directly manipulating or changing the our hardware or memory. So final insight, this will unlock everything. Your biggest gap was thinking everything reduces to values in memory. The missing half is where those values live, which is the location. So not everything actually evaluates the value. Some of that are just referencing location, such as the statements, right? The statement just hold it, it doesn't evaluate the value, hold the address. So that's actually how you reference as well. When you have a stock and return the address after the stock, you're basically returning the address in memory or references. First, what creating a programming language actually involves. A programming language is not just syntax like let x equal 10 semicolon. It's a system with three core parts. A. Syntax, what programs look like. Grammar rules, tokens, structure. So the grammar rules is the semantic. This is what the interpreter checks. And this is how the interpreter decides if it will provide an error. A tokens, so a way to convert that code into a node tree data structure AST. So it's a way to convert that into tree. So this token will be converted to string basically. Structure, this is actually the T, so this is where your parsers come in. B. Semantics. Sorry, a grammar rules is not actually a grammar. It's just a rules, or what syntax, what tool would you use to implement this type of grammar, right? Syntax. Semantics, what program means, what is a value, what is a variable, what does equal actually do. So equal is the assignment. It's really what we're really doing with equal is we're writing an instruction. So what is a variable? It's an identifier. Moving forward in the future videos, you will see that like a function. What is a function? A function is really doing two steps when we do like function and then parameters, which we will discuss in the future video. So what is a value? So what is a value? Value is just an irregular expression where you evaluate two. So that's different. I mean, we have two types of value, a location and a regular expression of value, to which it evaluates something. It doesn't store memory but an actual data. So that's a value. So this is where interpreters come in. So the interpreters comes in semantics and the parser come in syntax. So again, when we're parsing a syntax, we're really doing the first step of interpreter or compiler. We're really parsing, right? And then scanning is where the node tree data structure comes in, or AST. And then interpreter evaluates the string back to a value. Execution, how it runs. Evaluate expressions, manage memory or state, produce result. So it will evaluate now that AST or expressions, it manage the memory state and then produce the result. This is where runtime systems come in. So this is actually where the OS now carves out memory uh, to provide to that process. So where compilers or interpreters fit. Interpreter knowledge essential. You need to understand AST, abstract syntax tree, evaluation, environment, variables to values. So an environment is really how the variables map to a value. Without this, you can't define what does this language do. So you need to understand the abstract syntax tree where the after the parser, right, and then the interpreter and the environment at runtime, right? Because the process or the OS carves out a runtime like memory for this application. So how those variables map to a values at runtime when the app are actually running? How does the control flow look like? So without that understanding, the runtime, you won't be able. You actually won't be able to understand a language. That's why it's hard to learn programming language. So compiler knowledge important, but later you need to understand transformation, code to code. So another thing is that a Java, for example, has a runtime or interpreter written in C++. So as you can see, it's code to code. For and C, also C is different. It has a compiler that's also written in C. So what this compiler does is that it converts that user code that you wrote into an assembly code that an actual computer actually can understand. So it emits. So moving forward or in the next videos, we will discuss or we will provide an example on how the code, example code written to convert that programming language code written by developer to actual machine language. You will see that it's actually simple. It's just it's not as hard as you might think. It's just like a code as well, just like with what we've been discussing. It's just that those code are like automated, meaning that it doesn't it carves out data structure, and based on that data structure, that's how it will emit the predefined assembly instruction. Optimization, it's optional, so that's actually a part of compiler as well as that you will optimize, such as with what we discussed in the previous video, in which like the V8 engines find the most requested code and then optimize that runtime based on that frequently usage code. Code generation, optional. So this answers code generation, how do we run it efficiently? Minimum knowledge required, exact, not vague. To create a basic language, you need must know, non-negotiable, tokenization, scanner, parsing, AST building, evaluation, interpreter. So the scanner is actually in the tokenization, and the parsing, so the scanner is first and then next the parser. So let me correct myself. Scanner, parsing, and then interpreter. So the parsing is where you create the AST building. This is exactly what crafting interpreter teaches. Optional at first, bytecode, optimization, type systems, register, allocation. So this bytecode, we will discuss this, in which we will create like a virtual machine that will allow us to run that code or compiler code and run it to any hardware that we want. So these are compiler level concerns. Why you're feeling the difficulty based on everything you've asked, here's the real situation. You already understand OS, resource management, hardware, memory, CPU, execution pipeline, but now you need to understand how meaning is constructed before execution even matters. That's a different domain. So how meaning is constructed using the scanner and the parser. before the interpreter executes that. So that's a different domain. The key shift, this is the answer you're looking for. You've been picking program to CPU to memory to result, but language creation starts earlier. So we have text and then structure, the ASD. So that text is the tokenization, the parser, and then the structure is where the scanner um, code comes in, and then the meaning, it will produce the meaning, it will convert that string to a value, and then the interpreter executes that. So the interpreter blends into this meaning and execution, and the scanner blends into this structure and meaning. So as we will see in the future videos, this is just a code. Like an interpreter or compiler is just a code written in a code as well that transform a code into machine readable code. So common misunderstanding, important correction. Do I need compilers to create a language? Not exactly. You need interpreter level understanding, which is a subset of compiler knowledge. Deep truth, the one that matters. A programming language is not defined by how it runs, but by how its programs are interpreted, given meaning. Because your programming language could run in many different architecture, but how it is interpreted and then provide meaning instead of that 1 0 provides its unique taste. Final answer: yes, you need basics of interpreters to create a language. No, you don't need full compiler theory at the start. The critical skill is mapping syntax to meaning. So basically, you need to map, or you need to be able to skillfully create syntax that will produce expressive meaning. So that's what is one of the characteristics of successful language. Final insight connects to your journey. You already understand how programs run, O-step level. Now you're learning what programs are, crafting interpreters. So to really know what programs are or what language do, you need to understand how interpreter works. Clocks crafting interpreters to C, clocks VM, to GCC. So this is the this C clocks VM is the bytecode, the one running our bytecode, and that will be transformed by another program called GCC. So this GCC are written in C. So as you can see, we don't use the Java interpreter here, or JVM, which is written in C++, to compile our code. So we use a GCC which is written in C to transform it to assembly. Later we will discuss how, we will provide an example of this GCC code to convert our code to an assembly. So I'll walk you through it concretely with real code paths, not HandyWave. Where crafting interpreter stops. In crafting interpreter, clocks part, you end here, like switch instruction, then case of underscore add, and then double B, then push A plus B break. So this is C code, not assembly. This is your virtual machine. So this is an example of a virtual machine executing our locks code rather. So what GCC actually does to this real pipeline. So another thing is that since this virtual machine is a code and an interpreter that interpret our code is a code, as you can see, there's a lot of code. So first we have a code, and then the interpreter reads it, and then the code, there's a code that allows the interpreter to read it, which is our virtual machine. And then there is a code outside of that which is written in C that transform our code into an assembly language. What GCC does to this real pipeline, when you compile GCC VM.c-o clocks using GCC, the pipeline is C source, then preprocessing, then AST internal to GCC, then intermediate representation, IR, then assembly, then machine code, then CPU execution. Third, let's convert earlier clock's operation. Clock's code, read 1 plus 2, clock's bytecode. So this is how the VM convert that into a bytecode. Op underscore constant 1, op, and the next line op underscore constant 2, the next line op underscore add, the next line op underscore print. Clock's VMC code simplified. Case op underscore add colon, then open semi-curly bracket, then double B equal pop, open and close parenthesis semicolon, the next line double A equals to pop, open and close parenthesis semicolon, the next line push, parameter A plus B semicolon, then break semicolon, then closing semi-curly bracket. Now what GCC might generate? Simplified assembly. Now we go lower. A real simplified x86 to 64 assembly output could look like semicolon pop B, next line move rocks, comma, open square bracket stock underscore top, closing square bracket, next line sub, space stock underscore top, comma, 8, then next line semicolon pop A, then next line mov RBX. So mov is MOV, comma, and then open square bracket stock underscore top, closing square bracket, next line sub, then stock underscore top, comma, 8, and then next line semicolon A plus B, next line add rocks, comma, RBX, next line semicolon push result, then next line move, etc. So this is the connection you wanted. Layer locks, what happens, 1 plus 2, layer bytecode, what happens, op underscore add, layer CVM, what happens, A plus B, layer assembly, what happens, add rocks, comma, RBX, layer hardware, what happens, transistor switch. Fit, how this connects to inside the machine. And inside the machine, you learn registers, rocks, comma, RBX, ALU, arithmetic logic unit, instruction decoding. When CPU executes, add rocks, comma, RBX. Internally, first, instruction fetch from memory. Second, decoded by control unit. Third, ALU performs binary addition. So like this, 0001, open and close parenthesis, and then inside that is 1. The next line plus 0010, open and close parenthesis, inside that is 2. Then next line equals 0011, 1, open and close parenthesis, parameter 3. So that's what the actual CPU calculate. It's like a 001. So for results stored back in register. So that's what's happening in the CPU level. So full end-to-end pipeline, amazing mental model. So we have log source code, then a parser turns that into an AST, then compiler to bytecode, which is the clocks. It compile that to a bytecode, which is clocks. Then that bytecode runs in VM. So the one that compiles that to a bytecode is what? It's actually our interpreter, right? And then that interpreter, the one that it compiles, then pass it to a VM, which is written in C. So the written our VM in clocks is actually also written in C. And then GCC compiles VM. So the one written in C is also being compiled by the one written in C, which is GCC, to assembly. So the reason why C are the one used in compiling is because C are able to use or are able to access memory, file system, etc. So that's also why what Java abstracted. So if you do not know, C is the first language, then C++ improve on that language. It removes those like freeing memory and then accessing memory feature for the developer to easily develop code. Same with Java, it uses a class, it introduces classes just like with C. And then after the VM to assembly, and then assembly it's running in machine code, then CPU executes instructions, then transistor switch, which is the inside the machine.